Hello guys, welcome back to the channel Mathemagix JEE. In today's session, we are going to discuss the applications of infinite series expansions in solving JEE problems. We are going to see various applications of this concept in different chapters ranging from integration to summation of series as well as approximation of integrals. So, stay tuned with us till the end of this session. Here are some quick recaps of this infinite series expansions that will be used throughout the session. The expansions are noted here in these two slides. I will provide the slides in our Telegram group. From there, you can download the notes. So let's begin with a problem. It says the sum of this infinite series is what? Okay. So it is a very complicated looking series. Let us understand this series by expanding this first. So the series is saying that this series is summation r equal to 1 to infinity, then minus 1 whole to the power r plus 1, then it is 1 plus half plus 1 by 3 plus this is 1 by r times 1 by 3 whole to the power r. Now what will be our strategy to solve such questions? We will use the concept of infinite series expansions. So we know that the expansion of this log of 1 minus x is this. Log of 1 minus x is minus of x plus x square by 2 plus x cube by 3 plus so on. So if we can somehow manage to express this series in terms of this series, we can definitely solve this series. How? Because here are these harmonic numbers. These are called harmonic numbers. Summation of 1 by k from k equal to 1 to r is called the rth harmonic number. So basically, we can see a connection, a similar pattern of this log of 1 minus x expansion with this harmonic numbers. So somehow we have to manipulate the given expression to express this in terms of the log of 1 minus x expansion. And then we can substitute the value minus 1 by 3 here, as you can see, because here if we take this minus 1 common out of this summation, then we will be left with minus 1 whole to the power r times 1 by 3 whole to the power r. So we can see connection between x to the power r and this harmonic number. That means if we can somehow express this series in terms of some variable x, then we can put x equal to minus 1 by 3 in that expression to get the value of this summation. So let us first try by considering the series expansion of log of 1 minus x. So we know log of 1 minus x is equal to minus of x plus x square by 2 plus x cube by 3 plus so on up to infinity. And this is valid for minus 1 less than equal to x less than 1. Now if I take this minus sign here in this left hand side, we will be left with x plus x square by 2 plus x cube by 3 plus so on up to infinity. Now notice a very interesting thing, that if I multiply both sides by 1 over 1 minus x, so we get this times 1 over 1 minus x, and all of this is happening when x lies in this given range. So x is less than 1 as well as greater than equal to minus 1. Now let us consider this range, minus 1 less than x less than 1. Why are we going to consider this range? Because we want to expand this. Now what is this? If we can visualize this expression here, it is nothing but the geometric series, which is 1 plus x square plus so on up to infinity for mod x less than 1. So we are going to cut the domain of this expansion to minus 1 less than x less than 1. And obviously this minus 1 by 3 lies in this range, so our assumptions are valid. So if we expand this, it will be x plus x square by 2 plus so on up to infinity, times this will be 1 plus x square plus so on up to infinity. So this is what we have to use. Now if we multiply this two series here, we will get the coefficient of x will be simply 1 because no other terms will be there containing this x, then x square. Now see the interesting part, that if this multiplies with this, we will get an x square, but also when this x square by 2 gets multiplied with this 1, we will also get a x square term. So we will get x square by 2. That means x square will have two terms, x square and then x square by 2. So x square times 1 plus half. Similarly, if you observe the pattern, you will notice that for x cube, we will get three terms, 1 plus half plus 1 by 3. So we can say this will go to infinity. And all of this is happening when x lies in this range, open minus 1 to 1. So we can say by this expansion that minus of log 1 minus x divided by 1 minus x is equal to, this is x into 1 plus x square into 1 plus half plus so on up to infinity. So we can write this in sigma notation. It is equal to summation x to the power r times 1 plus half plus 1 by 3 plus so on up to 1 by r, where r is running from r equal to 1 to infinity. Now notice that this expression is similar to this expression except for a negative sign outside. How? Because here if you for some time assume that minus 1 by 3 is equal to x, then this series s infinity can be written as this minus outside, then this summation r equal to 1 to infinity, then minus 1 by 3 whole to the power r times 1 plus half plus so on up to 1 by r. So we can get the value of this s infinity by taking the negative of this expansion r equal to 1 to infinity summation x to the power r times 1 plus half plus so on up to 1 by r, evaluated at x equal to minus 1 by 3. So we can say this will be equal to log of 1 minus x divided by 1 minus x evaluated at x equal to minus 1 by 3. So it will give us, this will be log of 1 plus 1 by 3 will be 4 by 3, and then this denominator will be 4 by 3. That means our value of this series s infinity will be equal to 3 by 4 log of 4 by 3. So this is our answer. That means which option? Here, this option. Option B will be the correct answer for this problem. I hope you understood the concept behind this type of problems. You have to notice the pattern and try to manipulate the expressions to express the series in terms of some known series expansions. Let us see some other applications of this infinite series. So here is the second problem. It says given this integral, okay, so this integral is known as the Gaussian integral, which is minus infinity to infinity e to the power minus x square dx is equal to root pi. Then we have to find the value of this integral. Now there are two methods to find this integral. We will discuss two methods one by one, but first let us solve this question by infinite series method. So we are solving this by method 1. So here this integral minus infinity to infinity e to the power minus x square times cos of x dx can be expressed in terms of infinite series expansion of this cos x function. So it is written as minus infinity to infinity e to the power minus x square times the expansion of this cos x function can be written as minus 1 whole to the power n, then x to the power 2n divided by 2n factorial, where this summation is running over n from n equal to 1, sorry, n equal to 0 to n equal to infinity. So we can write this one as cos x equal to summation n equal to 0 to infinity minus 1 whole to the power n x to the power 2n divided by 2n factorial. Now, the interesting thing is that we can write this as minus infinity to infinity summation n equal to 0 to infinity minus 1 whole to the power n x to the power 2n times e to the power minus x square divided by 2n factorial dx. Why could we write this? Because this e to the power minus x square is independent of this variable n. Now here comes the most interesting part, that we can actually interchange the order of this summation and this integral. Why can we interchange the order of summation and integral? Because here, if we change the order, then integral of this will be convergent. So we consider this integral here minus infinity to infinity x to the power 2n e to the power minus x square and then dx. This integral will be convergent. There are many theorems to prove the convergence of an improper integral, but we are not going to discuss that because this is out of scope of our syllabus. But we can think this intuitively, that here this e to the power minus x square term will prevent this x to the power 2n term to grow exceptionally bigger. That means one time the function will get converged to 0 for x tending to infinity. So this integral will be convergent. So if we interchange the order here, it will become summation n equal to 0 to infinity, then minus 1 whole to the power n divided by 2n factorial times integral minus infinity to infinity x to the power 2n e to the power minus x square dx. So basically, we can call this integral here as a function of n, in, let's say. Now we have to determine the value of in. So if we consider this in here, it will be integral minus infinity to infinity e to the power minus x square times x to the power 2n dx. Now if we apply integration by parts here by considering this function as the second function and this function as the first function, so we will get e to the power minus x square times x to the power 2n plus 1 divided by 2n plus 1 with limits minus infinity to infinity, and then minus integral, then it will be minus and minus, so plus, then 2x e to the power minus x square times x to the power 2n plus 1 divided by 2n plus 1 dx. Now this integral will evaluate to 0 if you put the limits. So our integral will become 2 by 2n plus 1. This will be outside, and then integral minus infinity to infinity, then e to the power minus x square times x to the power 2n plus 2 dx. Or we can write this as 2 into n plus 1. Now this thing is nothing but I of n plus 1. So we derived a very important relation here, that I of n plus 1 is 2n plus 1 divided by 2 times I n. So from this relation, we can replace this n with n minus 1 to get I n equal to 2n minus 1 divided by 2 times I of n minus 1. So this is a important relation. Now, if we put n equal to 1 here, we will get I1 equal to, this will be 1 by 2, then into I0 or I0. Now, I0 is what? I0 is integral minus infinity to infinity e to the power minus x square dx, which is given to us in the problem statement that it is equal to root pi. So it will be root pi by 2. Similarly, if we continue to put n equal to 2, n equal to 3 and so on up to n equal to n, we will get in will be half times, this will be 3 by 2 times 5 by 2 times so on up to this 2n minus 1 divided by 2 times this root pi. So we can write this in here as this product of first n odd numbers can be written as 2n minus 1 times 2n minus 3 times so on up to 3 into 1 divided by how many 2's are there? Total n 2's. So times root pi. Now this we can rearrange further. If we multiply and divide by 2n, then 2 into n minus 1 times so on up to 2 into 2 into 2 into 1, then what will be this expression? We will get 2n factorial divided by 2 to the power n times, now how many 2's are there? There are n 2's, so 2 to the power n times here it will be n factorial, and there is also this root pi. So we get the value of in, which is equal to 2n factorial divided by, this will be 4 to the power n times n factorial times root pi. So we got the value of in is equal to this. Now we are going to substitute this value of in this integral, or rather in this summation. So we get our summation, let's call this s here, this s equal to this. So s will be summation n equal to 0 to infinity, then this minus 1 whole to the power n divided by 2n factorial times this in. So in is 2n factorial divided by 4 to the power n times n factorial. Now we can see this 2n factorial will get cancelled, and then we will be left with, there will be a root pi here also, I think. Yeah. So this we can write as root pi, then summation n equal to 0 to infinity. This we can write as minus 1 whole to the power n divided by n factorial times 1 by 4 whole to the power n. Now, why did we write this in this form? Because this expression is familiar to us. This is what? This, if we expand, we will get 1 by 4 whole to the power 0. So basically 1 by 1 factorial. So 1, then minus 1 by 4 divided by this 1 factorial plus 1 by 4 whole square divided by, this will be 2 factorial, and minus so on up to infinity. What is this? If we think about the expansion of e to the power minus x, it is 1 minus x plus x square by 2 factorial minus x cube by 3 factorial plus so on up to infinity. So this thing can be written as this root pi times this summation can be written as e to the power minus x evaluated at x equal to 1 by 4. So this becomes root pi e to the power minus 1 divided by 4. So our final summation here will be equal to root pi e to the power minus 1 by 4. This will be our answer to this problem. Now this was method 1 as we discussed. Now we are going for a second method to solve this same question. The second method is basically by using Leibniz rule, or rather I should say that by Feynman's technique, which is the method to evaluate some complex looking integrals. So basically we would introduce a parameter inside this integral. This integral is given to us as I minus infinity to infinity integral e to the power minus x square cos x dx. Now we evaluate this integral as a function of a, where this a will be introduced inside this cosine function. So it will become e to the power minus x square, then cos ax dx. Now we are going to use Leibniz rule. I already made a video dedicatedly on this Leibniz rule and how to apply this to solve problems. I will link the video in the description. You can check out that video to understand this Leibniz rule. So by Leibniz rule, we are going to differentiate both sides with respect to this parameter a. So we will get I dash a is minus infinity to infinity del a e to the power minus x square cos of ax dx. Now what was the purpose of this? Because if we are partially differentiating this function with respect to a, then we will get an extra x term here in front of this e to the power minus x square. Then we can club those two terms, and then e to the power minus x square times x will be easily integrable. So we perform this partial derivative here. We get minus infinity to infinity, then e to the power minus x square as it is, because x is considered as a constant here, times this will be minus outside, and then x times sine a x dx. Now if we club these two terms, this is nothing but some du. Now what is this u? This u is nothing but half time e to the power minus x square, and with a negative sign. So if we consider this as the second function here and this as the first function, we can apply integral by parts. So we will get it is equal to minus outside and then first function as it is times integral of this second function. So integral of this second function will be minus half e to the power minus x square with limits minus infinity to infinity, and then minus, then this integral, then minus half e to the power minus x square again. So this minus will become plus, and then e to the power minus x square times half, then derivative of this function with respect to x. So we will get a times cos of ax dx. So we can take this a outside here and like this. Now if we evaluate this integral, it will become equal to 0. So we can say that our I dash a will be minus then a by 2 times this integral. Now this integral is actually same as this IA. So we get this is equal to IA. Now what is this? This is a simple differential equation of first order. So we can write this I dash a as di dA is equal to minus a by 2 times I. So if we separate the variables, it will become di by I equal to minus a by 2 times dA. So we get this log I equal to, this will be minus a square by 4 plus integration constant. So I will be k times e to the power minus a square divided by 4. Now how to find the value of k. So basically this integral is a function of a. So we use this information here, that I of 0 is, if we put a equal to 0 in this expression, we get it is equal to minus infinity to infinity integral e to the power minus x square dx, which is equal to root pi as given in the question. So I of 0, if we put a equal to 0 here, we will get k, so it is equal to root pi. So we can say I of a is equal to root pi times e to the power minus a square divided by 4. Now here we have to find the value of I of 1, because here if we put a equal to 1, we will get this integral. That means we get the value of I1, which is equal to minus infinity to infinity e to the power minus x square times cos x dx. It will be equal to root pi e to the power minus 1 by 4. So this will be our answer. I hope you understood both the methods to solve this problem. Now the next application of this infinite series expansion is about approximation of integrals. So this is a PYQ of JEE Advanced. It was asked in JEE Advanced 2020. Which of the following inequalities is oblique are true? So we are given four inequalities, and this is a multiple correct type question. So we have to tell which of the inequalities are true. Okay. So first let us begin with option A. Option A requires us to find the integral 0 to 1 x cos x dx. Now the problem with this integral is we cannot directly evaluate this. So we have to approximate this integral. So we have to go by infinite series expansion method. Now we know that cos x is 1 minus x square by 2 factorial plus x to the power 4 divided by 4 factorial minus x to the power 6 divided by 6 factorial and plus so on. Now we can observe a very interesting thing here, that as in all cases here a, b, c, d, the limits of x are 0 and 1. From this expansion we can say that cos x should be less than 1, because some positive quantity here is being subtracted from 1, and definitely the magnitude of this is greater than this term and this term, because x square is greater than x to the power 4 if x belongs to 0 to 1. So cos x should be less than 1, and this is absolutely true for x not equal to 0. So if we include the case x equal to 0, we will say cos x should be less than equal to 1. Similarly, we can say that cos x should be greater than equal to 1 minus x square by 2 factorial. Similarly, from here we can further say cos x should be less than equal to 1 minus x square by 2 factorial plus x to the power 4 divided by 4 factorial, and similarly we can derive further inequalities. Now how to apply these inequalities to establish this inequality here? So we can say that cos x is greater than equal to 1 minus x square by 2 factorial. Why are we choosing this case? Because option A needs us to compare whether this integral is greater than equal to 3 by 8 or not. So we choose this case. If we multiply both sides by x, then x cos x should be greater than equal to this times x, and inequality sign will remain unchanged because x lies between 0 and 1. So x is definitely positive or can be equal to 0. Now if we integrate both sides with respect to this variable x, we get this integral 0 to 1 x cos x dx is greater than equal to this integral. If we solve, it will be integral 0 to 1 x minus x square by 2 factorial this will be x cube, by the way, times dx. So this will be half minus, this will be half times 1 by 4. So it comes out to be this integral 0 to 1 x cos x dx is greater than equal to, this will be 3 by 8. So option A is definitely true. Now we need to check other options. So for option B, if we check similarly, it is saying 0 to 1 integral x sin x dx is greater than equal to 3 by 10. That means if we check for this, we need to use the infinite series expansion of sin x. So we know sin x is x minus x cube by 3 factorial plus x to the power 5 divided by 5 factorial minus x to the power 7 by 7 factorial plus so on. So we can say by the same logic that sin x is less than x or equal to x if x is 0, and then sin x is always greater than equal to x minus x cube by 3 factorial. Similarly, sin x is less than equal to x minus x cube by 3 factorial plus x to the power 5 by 5 factorial and so on. So we can say this sin x times x will be greater than equal to x into x minus x cube by 3 factorial dx if we integrate both sides. So if we solve this, this integration will be greater than equal to integral 0 to 1 x square minus x to the power 4 by 3 factorial dx. So this comes out to be 1 by 3 minus, this will be 1 by 6 times, this is 1 by 5. So it comes out to be 1 by 3 minus 1 by 30. So 1 by 3 into 9 by 10. That means 3 by 10. So integral 0 to 1 x sin x dx is greater than equal to 3 by 10. So we can see option B is also true. Now in option C and D, it says similar kind of expressions but with x square. So here if we check this C option, it is saying integral 0 to 1 x square cos x dx. So if we go by the same method, that we need to somehow try to establish this inequality or check this inequality whether it holds true. So we can say by the same logic that integral 0 to 1 x square cos x dx will be greater than equal to integral 0 to 1 x square times, it will be 1 minus x square by 2 factorial dx. So if we solve this right hand side integral, it will become integral 0 to 1 x square minus x to the power 4 divided by 2 factorial dx. So it will be 1 by 3 minus 1 by 5 into half, so 1 by 10. That means 7 by 30. Now 7 by 30 is almost 0.2 something. But in the question, it says this integral is greater than equal to half. So we cannot tell whether this option is true or not by this method. We cannot directly say whether it is correct or not, but we can check by another method. So let us say that integral 0 to 1 x square cos x dx. Now this integral will be always less than or equal to integral 0 to 1 x square dx. How? Because we discussed that cos x is less than equal to 1. So this right hand side integral, if we evaluate this, it will become 1 by 3. So we know integral 0 to 1 x square cos x dx will be always less than equal to 1 by 3. So we know 1 by 3 is almost 0.33, but here the option is saying that this integral is greater than equal to half, which is 0.5. So These two conditions cannot simultaneously become true. That means option C is wrong. Now we have to check the option D. So for option D here, if we check this integral 0 to 1 x square sine x dx, this integral is greater than equal to integral 0 to 1 x square times x minus x cube by 3 factorial dx. So this integral, if we evaluate, it will become integral 0 to 1 x cube minus x to the power 5 divided by 3 factorial. So 3 factorial is basically 6. Then if we integrate this, it will become 1 by 4 minus 1 by 6 into 1 by 6. So 1 by 36. So it will become 36 and 8. That means 2 by 9. So integral 0 to 1 x square sine x dx is greater than equal to 2 by 9. And this option D is also saying that this integration is greater than equal to 2 by 9. So option D will be also true. That means the correct answer will be A, B and D. I hope you understood the concept behind this problem. How we can use infinite series expansions to approximate some integrations. Now, here is a question for you. This was asked in JEE Main 2021. This is also based on the approximation of integrals by infinite series expansions. So definitely give it a try and post the answer in the comments.